Okay, so let's look at some practice problems for eigenvalues and eigenvectors. This is drawing materials from both chapters 7 and 15. We're not going to stick to just 2D, so let's go through both of them. Let's start with a 2D problem, though. Find the eigenvalues and eigenvectors of this matrix A equals 1 minus 2 minus 2, 1. Work out both the eigenvalues and the eigenvectors, work through your solution, and then come back and watch the answer. Okay, so hopefully you had that. It's a pretty simple problem. First, we will form the matrix A minus lambda I. We then take the determinant of that. We get our characteristic equation is 1 minus lambda squared equals 4. We can now use the quadratic formula to get the roots of that are 3 and 1. Now to get the eigenvectors, we take A minus lambda times I. That gives us a matrix. And we now want to solve this matrix, the homogeneous form of this, x equals 0. If we go to do that, we go to do the first thing, we see these two rows are dependent, one of them disappears, so we can arbitrarily set one of them to the value 1, set the bottom row to 1 after it's gone, and then we'll solve the top value has to be minus 1, and that gives us that our eigenvector is 1 over the square root of 2 times minus 1, 1. The 1 over the square root of 2 because we like to put them in normalized form, so the length of the vector has to be 1, so we do this. But any multiple of minus 1, 1 will actually give us our eigenvector associated with the dominant eigenvalue, which is equal to 3. Our second eigenvalue is 1. We put that in, do A minus lambda I. We get our matrix is 2, minus 2, minus 2, 1. In this case, we can solve that homogeneous equation. We get 1, 1. And again, we want to make it a unit normal, so we get 1 over the square root of 2. So take our equation, form the characteristic equation by taking the determinant across A minus lambda I. Then we take the resulting roots, stick them back into A minus lambda I, solve the homogeneous form, and get our eigenvectors. Okay, so let's do a larger problem. See if you can find the eigenvalues and eigenvectors associated with this. Okay, with a 4x4, if your first thought was, I don't know how to do this, it's too big, and you want to go use MATLAB Octave, that would get you an answer, but there's lots of special cases, and this is one of them. This is an upper triangular matrix, so the on the diagonal, if I do our cofactor expansion, remember what that was from chapter 15, the diagonal has the upper triangular or triangular matrices have the special property that the diagonal are the eigenvalues. The eigenvalues are just 10, 1, 0.1, and 2. Now that gives us the eigenvalue for the dominant eigenvalue, which is 10. The eigenvector is solving the problem A minus lambda I, where lambda is 10, which gives us a matrix whose first column is all zeros, and then these other items over here. But since the first column is all zeros, we know we can actually arbitrarily choose the first item to be 1, and because all the rest of the matrix has got values in it, we need them to be 0 to be able to solve our solution, and so this gives us for an eigenvector of 1, 0, 0 transpose for our eigenvector associated with the largest eigenvalue. So despite the fact this was 4x4, using the known properties of triangular plus the fact that this was a generate system made this one pretty easy to get this largest eigenvector. Next one's a little harder, so we'll skip over that and leave that. If you get to a 4x4, go for a tool to compute it for you. Understanding how those tools work, let's look at the power method a little bit. So consider the matrix A given here, starting with the vector R1, which is 1, 1, 1, some random starting point. Carry out 3 steps of the power method to determine A's dominant eigenvalue. Okay, so hopefully you remember what the power method was. If not, look it up, then try it, work through what it is. It'll help you remember it. And so once you know what the power method is, it's actually pretty simple. We're just going to take this vector R, multiply A times R, and we'll get the value 353. 535. And then the power method is we take that result, we multiply it by A again. In this case, we then get 25, 13, 21. Take that result, put it back in, multiply again, we get 121, 55, 93. Now, if I look at the ratios of these things, I start getting beginning of my answer. So the ratios for each of these three elements gives us 4.8, 4.23, 4.43. So we're not quite converged. The dominant eigenvalue actually has a value of 4.64, but you can sort of see if you look at these other ratios, here the ratio was 5.35, and now it's 4.8 to 4.23 and 4.43. So it's converging, and eventually, after a number of iterations, it'll be down to the actual answer of 4.646. So let's use our eigenvalues to help us solve problems. So let's consider the eigenvalues of the matrix A and the matrix A to the 10th. So hopefully you quickly recognize that this is, again, the special triangular form. So the eigenvalues here are just 2, 2, and 1, just reading off the diagonals. And I surely hope that you recognize that you don't really want to compute A to the 10th by multiplying A times A times A times A times A times A, but to recognize that the eigenvalues of A to the 10th are the eigenvalues to the 10th power. So I can just take 2, 2, and 1 and raise them to the 10th power. I get 2 to the 10th, 2 to the 10th, 1, which if you did it with a calculator would be 1024, 1024, and 1. So eigenvalues of powers are easy to get to. So now let's do a full-blown, this one's not going to be as easy. It's a full 3x3, but there's no special properties here. So compute the eigenvalues and the eigenvectors of this matrix. This matrix is not symmetric. It's not any special form, but so you're going to have to work through this one, the long form. Okay, hopefully that you've been able to work through that. So the first step is, of course, to take the determinant where we take lambda down the diagonal. So we get the determinant of minus lambda 0, 1, minus 2, 1, minus lambda 1, and 2, 0, 1, minus 1, minus lambda. We take that, we're going to do our determinant. Again, there's lots of ways of looking at the determinant. This time I'm going to do it sort of in a cofactor expansion. So I'm going to take minus lambda times the determinant of the 2 by 2 subblock below it. So I get minus lambda times the determinant of this 2 by 2 minus the quantity 0 times the determinant from the other cofactor, minus 2, 1, 2, minus 1, minus lambda. And then the last one is 1 times the determinant of the 2 by 2 element that's there. And that gives us overall, work through the algebra, we get 3 lambda minus lambda cubed minus 2, which we can factor. If you're not good at factoring cubic polynomials, one of the things you can recognize is if there's going to be an integer solution, the integers that you have to divide the number that's your constant here. In this case, it's 2, so the only integers we can do that with are 1 and 2, and just trying 2 plus lambda, factor that out, and then you see that the other's got to be 1 minus lambda squared. So this gives us our solution, and that gives us our roots minus 2 and 2 roots of lambda equals 1. Now we need to go find the eigenvectors. If you didn't find them yet, go do it now, and then we'll continue on with that. Okay, so to find the eigenvectors, we plug in our eigenvalue. We do A minus lambda times I, which in this case gives us the matrix 2, 0, 1, minus 2, 3, 1, 0, 2, 0, 1. For this, we want to then solve this matrix times x equals 0. We go to solve this. The first thing we notice is the top row and the bottom row are exactly the same, so it cancels out. We can also row reduce this one here to get an upper triangular form by just adding those two. So we get this as our upper triangular form. The bottom row is 0, so what does that tell us? Well, if the bottom row is 0, it tells us we can arbitrarily set the last item to anything we want, and the other two are then just solved by back substitution in these, and we get the constraints minus 1/2 x3 minus 2/3 x3 and x3. We can fill any value we want, any multiple of that as an eigenvector. We like to normalize, so we're going to normalize by the length of that vector, which is 0.76822 times that vector, giving our canonical eigenvector associated with lambda equals minus 2. Now for lambda equals 1, we do something similar. This is a double root, but that doesn't matter. We still go ahead and solve it. We're just going to get 2 answers out of it. So we subtract down our diagonal. This one's a little bit more complicated to go through your Gaussian elimination. You can see the last row, if we just add 2 times the first row, again it disappears. The middle row, we subtract 2 times the first row. We get this as our upper triangular form. In this case, we go to fill them in, and we notice that it's the second column is now 0. So we get that x2 is any value we want, and the other 2 values are going to be 0. So we can now figure that in. So we can fill in 0, 1, 0, because the other constraints are all 0. We actually get 2 eigenvectors of 0, 1, 0. And if we wanted to truly orthonormalize them, we could add another one of to normalize them, but this gives us our second eigenvector for the double root, lambda equals 0. Okay, another one, this one looks special and it does have some special properties, but try and find the eigenvalues of this matrix, but be careful. Okay, so while this is special, hopefully you didn't just say, well, it's diagonal so I can take it, because it's not a diagonal. This is a inverted diagonal, the reverse diagonal form. So in this case, the eigenvalues are -2, -1, 1, and 2. You can do this, but you have to do sort of row exchanges. I have to exchange the top row and the bottom row and exchange the middle two rows. And then I got to keep track of, as I exchange rows, row exchanges change the signs of eigenvalues. So you have to be careful what's going on with those. Just to sort of show it to you and also see what happens to the eigenvectors, because you might think the eigenvectors are the identity matrix, but they're not. Because as we did those row exchanges, the eigenvectors become coupled on the top and bottom rows. So our first eigenvector has got 1 over the square root of 2 with 1, 0, 0, 1. The middle ones, we have 2 of these where we again exchange 2 rows. And so we sort of see that even though this looks very special, and it is quite special, you can get to the eigenvalues, but you have to remember that the coupling of rows by exchanges changes both the sign of the eigenvalues and couples the eigenvector elements together. So we get a more complicated solution. For our last problem, a little bit more theoretical type problem, showing your understanding. So let lambda be an eigenvalue of a matrix A. Show that the matrix A plus I has an eigenvalue of lambda plus 1. So don't have to be a completely formal proof, but hopefully you were able to put that together and getting a statement that would look enough like a proof to convince me you know how to do this. So if we just make up or assume R is the eigenvector corresponding to lambda associated with A, it exists. Every eigenvalue has an eigenvector. Well, now let's just use that for a second. We're going to take A plus I times R, and let's see what that equals. That's equal to A plus R, because I can just multiply in, I can distribute, plus R. But that's equal to, since AR, it's an eigenvector associated with lambda, is just lambda times R plus R. Now I can factor the R back out, and I get lambda plus 1 times R. So I get that A plus I R equals lambda plus 1R. Therefore, lambda plus 1 is an eigenvalue associated with A plus I, and it has a corresponding eigenvector R. So that's enough of our problems. If you struggle with these, again, chapters 7 and 15 have multiple problems at the end. Work through some more problems, seeing if you can derive the answer in the back of the book until you can do them cleanly, and you'll have mastered this eigenvalue, eigenvector material.